Hello, everyone, and welcome to our lecture videos on logical quantifiers. So, logical quantifiers are a powerful way to combine what we already know about propositional logic on the one hand and set theory on the other. So we're going to jump right into a motivating example, and then we're going to go through the syntax a little more carefully. So suppose that I have a set here of students in discrete math class, and we're going to imagine a very small class that has only 4 students whose names are A, B, C, and D. And what I want to do is I want to form some logical statements that describe the state of knowledge of set theory in this class. And so I have a proposition, or rather a predicate, P of X, and the predicate P of X says that X, whoever that is, knows set theory. And so, for example, I might hope that student A knows set theory, and so if I fill in the proposition here, this would be that A knows set theory. But suppose now that I don't want to just sort of think about individual students. I actually am wondering about the entire class. And so I'd like to be able to say questions like, or say statements like this. Somebody in discrete math class, and I don't know who it is, but someone knows set theory. How would I say that? One way to say this, that someone in discrete math knows set theory, would be to use tools that we have already learned. Because I can say this using disjunctions or operators. Because saying that someone knows set theory means that, well, either A knows set theory or B knows set theory, or C knows set theory, or D knows set theory. This is a correct translation. This works. That's true. But this is a little bit limited. First of all, that's a lot of writing for me to do. And second of all, if another student adds the class, or indeed if one of these students drops the class, then my statement will no longer correctly describe the students in discrete math class, because A, B, C, and D will no longer be the correct set of students in the first place. So, if I want to express this proposition Q, someone in discrete math knows set theory, I can use a different, new, special logical symbol. This logical symbol looks like a backwards E, and I pronounce it there exists. There exists. We're going to go over the syntactic details in a moment, but I'm just going to move ahead for now. I say there exists an X in the set D, this is D, the set of discrete math students. There exists an element of the set D that I'll call X, such that is often written with the colon here. There exists an X in the set D such that P of X is true. So this way to express the idea, I'm not writing out P of A, P of B, P of C, P of D. Instead, I'm using this fancy new syntax to say there exists some element of this set, I'm not sure which one. There exists some element of this set D, and I'm just going to give that hypothetical element a name X. There exists an element of D with the property that P of X is true. Or a little more concisely, there exists X in D such that P of X. Let's do one more motivating example to introduce our other logical quantifier, and then we'll go into a little more detail on how to construct these statements. So now let's look at a different example. This time, I want to say that everyone in discrete math class knows set theory, which is definitely true because you watched the last videos, right? Right. Okay. So how would I say that everyone in discrete math class knows set theory? Similarly to before, there is a way to do this using operators that we have already seen. Because if I'm saying that everyone knows set theory, what I'm saying is that student A knows set theory, and student B knows set theory, and student C knows set theory, and student D knows set theory. So nothing wrong with this, except again, this is a lot of writing for me, and I'm going to have to keep track of if students add or drop. I'm going to need to change my statement because I'm enumerating explicitly all the elements of my set, and that's a bit of a hassle for me. Similarly to before, we have a special syntax that allows us to write this more concisely and in a way that will still be correct as a statement of R, the proposition that everyone in discrete math knows set theory, even if someone adds or drops the class. So this time I use this funny symbol which looks like an upside down A, and this symbol is pronounced for all. For all. Similarly to before, I say for all x in D, so for every element of this set D, for all x in D, it's the case that P of x. For all x in D, P of x is true. So with these two new symbols here, there exists and for all, we can concisely express more complicated logical ideas by quantifying over every element in a set. So let's go ahead and dive in a little more detail into how these expressions are constructed, and then we'll look at some examples. So how do we construct these statements? Let's break down the syntactic pieces of these statements using the there exists and for all operators. Let's start with there exists. So last time we saw an example of a there exists statement, and I'm going to write the same one. I'm just going to color code it this time. So we had the there exists symbol, the backwards E. That's the especially new part. Then we had a set membership. We said there exists an X in the set D. Then finally, such that with the colon, P of X. Okay, so four total pieces here. Four total pieces. I've color coded them with four colors. So if I'm translating this, what I'm saying is there exists, that's my operator, an element X of the set D such that, we could also say with the property that, P of X is true. So this is my complete statement here. There exists an element X of the set D such that P of X is true. Now, something that I really want to emphasize here is that all of these pieces are important. All of these pieces are important. It's easy to remember the there exists piece, the funny backward E. We usually remember that one pretty well. But all of these pieces are important, and in particular, a piece that's often forgotten is the set membership here, X in D. So it's easy to forget about the in D part and write just there exists X such that P of X. But this isn't really right in any context because I need to know what the possibilities for X are. If I want to say that someone in my discrete math class knows set theory, then I need to say, oh, I'm talking about all the x's in my discrete math class. If I just say there exists x, I don't know what set I'm referring to. Is that someone in discrete math class? Is that someone in the world? Is that possibly extraterrestrial life in the universe? I need to say what set I'm talking about. And so for this reason, there exists X in D. I always have to say what that set is in order to have a correct logical statement. And this means that often I might need to define the set for myself. So if I want to say there exists a student in my discrete math class who understands set theory, then I need to say, oh, D is going to be my set of discrete math students. Similarly, I have to define my predicate. P of X is my predicate that student X knows set theory. I need to define these things and say them explicitly in order to create correct logical statements. Let's do for all. So that's the other logical operator that we just introduced. So I'm going to do similar color coding. This time for all x in the set D. In the set is very important here as well for the same reason. P of x. Okay, so how would I translate this? For all x in the set D, P of x is true. Okay, so a few translation points here. First of all, we don't really need a such that when we're translating for all. And that's not really a logic thing, that's just about how English language works. It's not really a deep math point. Because of this, I really like to emphasize such that when I am working with existential quantifiers, there exists. And because of that, I use colons that really remind me to say such that. But for all, I often write just a comma. Um, I don't care too much whether you use the exact punctuation here, colon or comma. I don't care too much if you use the exact punctuation that I do. Just make sure that you're using some kind of punctuation consistently. That's fine. But here, for all x in the set D, P of x is true. Another way to say this that means the same thing is that every element x in the set D makes P of x true. That's an equivalent way to say the same thing.